those two elements is much greater in iodine monofluoride than in chlorine monofluoride. So because of that, the larger dipole moment has to be in iodine monofluoride. But now we could also do something where we're calculating or quantifying dipole moment. So for example, I gave you the bond length in HCl, hydrochloric acid, is 1.27 angstroms. In part A, I want to calculate the dipole moment in device that results if the charges on the H and Cl atoms are +1 and -1 respectively. So we have H, we have Cl. The distance separating them is 1.27 angstroms. And an angstrom, which we should know, is 1 angstrom is equivalent to 1 × 10 to the -10th meters. So really, I want this in meters because remember, a debye is a coulomb meter. So I need this not in angstroms, I need this in meters. So really, this would be the same thing as saying 1.27 × 10 to the -10th meters. So hopefully we all agree on that. That would be the R in our formula because they're asking us in this question to calculate the dipole moment. So I know that this would be that distance separating them because that's the bond length is what they told me. So this is my R. R equals this. And they gave me charges. They say, let's have this one be a +1 and chlorine would be a -1. But remember, we give a +1 and a -1. We make it simpler in chemistry, but really that's indicating like charge of electrons. So it's not just a +1 or a -1. If you look in the back of your book, you would see that an electron has a charge of let's write this down. Let's say charge. Actually, let's do Q, sorry. Q equals my charge of the electron equals 1.60 times 10 to the -19th coulombs. So 1.60 times 10 to the -19th coulombs. So when we say a +1 or a -1 charge, we're saying that this -1 is really just 1.6 times 10 to the -19th coulombs. If something has a -2 charge, it's 2 times 1.60 times 10 to the -19th coulombs. So because it's always in multiples of this number, it's just easier for us to say this has a -1 charge, this has a -2 charge, because really this is the overall charge of that electron. So we just want to make it simpler for us, and we do that instead of saying, oh, chlorine has a charge of 1.60 times 10 to the -19th coulombs. It's easier to just think about this in terms of multiples, which is what we do, +1, -1. So if I know that this is the charge then, I want to find dipole moment here. So let's find mu, which is charge times my distance that's separating them. So we know the charge here is 1.60 times 10 to the -19th. So I can take that times, I'm going to take this and multiply it by 1.27 times 10 to the -10th meters. So if I multiply those two together, I'm going to get, I don't know because I don't have a calculator. There we go. Well, you're going to get something. You're going to get something in coulomb meters. So whatever answer you get here in your coulomb meters, we need to convert that to debye's because we want our dipole moment to be in debye's, not in coulomb meters. And we know that in 1 debye, there's 3.34 times 10 to the -30th coulomb meters. So whatever you get as your answer here, you're going to divide that by our factor here, and you should get an answer of 6.08, I think. Yeah, you should get an answer of 6.08, and then we'll symbolize that D, debye's. So that's our dipole moment. That's how we have quantified polarity here. So we can quantify polarity by using something called the dipole moment. In terms of The next one, it says, the experimentally measured dipole moment of HCl is 1.08. That's what they found in an experiment. What magnitude of charge then, if we're thinking about it in units of E, if we're thinking about it as that 1.60 times 10 to the negative 19th, on the H and on the Cl atoms would lead to this dipole moment. So in this case, I'm trying to find, they gave us dipole moment. We already know, we also know the distance separating those, so we could find charge here. I could find coulombs, but I want it also in terms of E. I would like you to try this one on your own for me, and I want you to bring that. I'm checking it first thing at the beginning of class tomorrow, guys, so try this one for me, and we'll check it. We'll go over it as well at the beginning of class. In terms of polar covalent bonds, if we see the greater the difference in electronegativity, we know then that that also means the more polar the bond will be. So the greater the electronegativity difference, we know also the more polar that that bond will be. I can also notice, though, that as we move from HF, because this is going from HF to HCl to HBr to HI, so we're just moving down the halogens in this case. So we have HF, HCl, HBr, HI. I can notice here that as the electronegativity difference is decreasing as we're going across here, what happens to the bond length? As the electronegativity difference is decreasing here, I can see here that the bond length is actually getting bigger. So as electronegativity difference decreases, the bond length is increasing. The electronegativity difference decreases the amount of charge separated, which is causing the dipole moment to decrease, even though the bond length is increasing. So let me say that again. The electronegativity difference decreases the amount of charge separated, causing the dipole moment to decrease, even though bond length is increasing. We can see this for molecules with an electronegativity difference has a greater effect on dipole moment necessarily maybe than bond length. So let's go to this last thing here before we get to Lewis structures, differentiating between ionic and covalent bonding. So we treat ionic and covalent bonding separately. And if we think about covalent bonding, we think about molecules. They are non-electrolytes, meaning that they don't, if we dissolve them in water, if they dissociate, they don't dissociate in water into ions. So they have a non-electrolytic behavior. They also have low melting and low boiling points. Ionic bonding, they have brittle and extended lattices. They're malleable, they're ductile, they have high melting solids, and they're very electrolytic, meaning that if I dissolve them in water, they can dissociate into their ions. So how can we recognize the type of bonding? Let's try to figure out different relationships that we can think about here. In terms of recognizing them, we have a metal versus a metal and a non-metal, we know, is an ionic bond. If we think about also a metal and a polyatomic ion would be a huge indication that it's an ionic bond. Versus two nonmetals. Two nonmetals would give me a covalent bond. I have a molecular compound there. But there are gray areas that this kind of lies in between. So we'll talk a little bit more about that tomorrow when we do some practice. And then another way that we can recognize is by or through electronegativity difference. So we need to make sure that this being an ionic bond to polar covalent to non-polar covalent, it's a continuum. It's not something that's just so much cut and dry. We'll see that it's definitely a continuum. And I think I'm having right now a plan that we may possibly do a POGL on this tomorrow. Okay, Lewis structures. In terms of Lewis structures, we always know that Lewis structures were developed by Gilbert Lewis. He also thought about Lewis acids and bases, but Gilbert Lewis wanted to come up or create a way that he could keep track of all of the valence electrons, because to him he thought It's these outermost electrons that are really the reason that we have bonding. So let me keep track of them by drawing those or representing those as dots. So our Lewis dot structures or Lewis structures we get from Gilbert-Lewis. So in terms of hydrogen, we know hydrogen has one valence electron. If we have H2, so for a diatomic molecule, we would have these two come together and share that bond. So we could draw it with the two dots, or we could have written this as H, because remember the one dash here is representative of 2 electrons. So we could have written it either way. Chlorine, we know each has 7 valence electrons. So if we have our diatomic element here, chlorine, then they can share that pair, so then that's what keeps them together to be stable as my diatomic element there. And again, if they're sharing that, we can represent it as that single line, because that single bond is representative of 2 electrons. So not all Lewis structures, though, are going to have single bonds. We could have a double bond, or we could have a triple bond. So in our diatomic nitrogen molecule, for example, let's look at that one. So we have N and N. I want to write, first of all, just the Lewis structure of each individual nitrogen atom. So I would have 1, 2, 3, 4, 5, because nitrogen has 5 valence electrons. I'm going to do the same thing over here. 1, 2, 3, 4, 5. Okay, well these unpaired electrons here, I could have something come in there and they could share, or we could bond something here. So maybe nitrogens, they could share these two, maybe these nitrogens could share those two, and then maybe they can share, maybe I can have it where they're going to share these. So I'm going to have 1, 2, 3 bonds that are shared in between those nitrogens, leading then to my triple bond. And they still have that lone pair of electrons above each of them. So this would give me, for example, then what my diatomic nitrogen would look like. So in that case, we can see there that they would have a triple bond. Carbon dioxide, we can do that one too. Let's look at that one. So carbon dioxide, we have CO2. If we found the number of valence electrons that it has, we know carbon has 4. And I know oxygen has 6, but there are 2 of them. So that really means that there are 12. So overall, I need 16 valence electrons total. I need 16 electrons in this Lewis structure. So carbon would be my least electronegative element, so COO. So here's my skeletal structure. Now we said we count valence electrons, we figure out the central atom, we've done that. We make a skeletal structure with single bonds first. So then we have to fill up the octet on the outer ones. So we want to do that first. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have all of 16 of my electrons that are accounted for. And the oxygens have 8, but just carbon, my central atom, have a full octet. It does not. It needs to have some more bonds here to make sure it has that full octet. So oxygen, I'm going to take that lone pair and give it to carbon. I can take this lone pair and give that to carbon. And then if I do that, those become bonds. And let's see what changes then now. So now I would have C, double bond O, double bond O. And since I just took off one lone pair, I still have 2 remaining ones on oxygen. So 1, 2, 1, 2. Let's check this. So in this case, we have oxygen is 1, 2, 3, 4, 5, 6, 7, 8. It has 8 around it. 1, 2, 3, 4, 5, 6, 7, 8. So I see that oxygens have that stable octet. I also see that carbon has that stable octet. So this would be my Lewis structure for carbon dioxide. And we could calculate formal charge on this as well. So let's do that because it's a really good way to check to make sure that this one wasn't right at all, but this was the one that I really wanted. So in this case, we know oxygen has 6 valence electrons, and if I think just about the electrons that are around it, 1, 2, 3, 4, 5, 6. So 6 minus 6 gives me 0. For carbon, it has 4 valence electrons. If I look at it, it has 1, 2, 3, 4 around it, 0. If I do the same thing for this oxygen, I should still get 0. Formal charges of all 0 means that we're going to have a nice, stable Lewis structure. We don't even need to do the formal charge on this one because we can tell right now if carbon has a valence electron count of 4 and I only have 2 electrons by it, that's going to give me a positive 2 charge here on the carbon. If we did, we can just do the oxygen one too. We know oxygen has 6, but we have 1, 2, 3, 4, 5, 6, 7. So that oxygen would end up having a -1. Same thing over here. So since those don't have 0, it's not nearly as balanced or as stable as that one is. And we can see that through doing formal charge. Okay, so in terms of relationships between bond length and number of bonds. Actually, guys, this is slide 25. Highlight this one for me. We'll start with this one tomorrow in class because I want to get through at least to the Lewis structure stuff, which we've already done examples of, but just at least that we've gone through the rules. So in each class, someone please remind me that we need to go over slide number 25. That's somebody's job tomorrow, so we need to go through slide 25. Okay, so starting with rules for writing or drawing Lewis structures. First thing, sum up all of the valence electrons in the atom. I want to make sure that if it's given a charge, if it's an anion, I'm going to add an electron for the negative charges. So like, for example, we had PO4, and that has a -3 charge. So we know that oxygen has 6, but there are 4 of them. So technically that's 24. And then we know that phosphorus should have 5. So we have 5 plus our 24, but I have 3 extra electrons, so that's +3. So it's really my 24 plus 8. So overall, phosphate has a total valence electron count of 32. So when they're saying, if it's an anion, make sure you're adding the electrons if it's negative, and if it's a cation, it's positive, that means we're taking an electron away. So first things first, find the sum of the valence electrons. Next thing, figure out the central atom. The central atom should be the least electronegative element, and it cannot be hydrogen. Once you figure out the central atom, you want to connect then the outer atoms that are bonded to it only by single bonds first. So we're only single bonding these elements to that central atom first. With that being said too, well, we'll get to that in a minute. Okay, next step. So found valence electrons, we found our central atom. Guys, this is called a skeletal model or a skeletal structure of the compound because we don't have any electrons on there yet. So this is just the skeletal structure for PCl3. The third step would be to complete the octets on the outer atoms first. And remember that hydrogen only has a single pair of electrons around it. So hydrogen, remember, is that special little guy. So I have chlorine around this phosphorus, so we added the extra electrons around chlorine here, and down here we were keeping track. So when we found our total number of valence electrons, we found that it was 26 in PCl3, because we have 7 for one chlorine, but 3 of them, so that's 21, plus 5 more would be 26, so that's how we got 26 here. By giving 3 bonds, remember 1 bond represents 2 electrons, so we have 26 minus 6. So now I have 20 valence electrons I still have to account for. I added 18 more because I gave 6 electrons to each of those 3 chlorines. So now I have 2 electrons that are remaining here. So then I can I need to make sure my chlorine atoms have a full octet. But my phosphorus did not have a full octet. So I can give that a full octet by placing any leftover electrons on that central atom. If I run out of electrons, so let's say that I'm drawing my Lewis structure and I'm like, oh no, don't have any more valence electrons, but I still need some. So if I run out before that central atom has its octet, that's when we're going to start forming multiple bonds. So we have HCN in this case. And let's look at that one. So in this case, HCN, carbon would be my central atom here. I know that hydrogen, there's 1. Carbon, there's 4 valence electrons. Nitrogen, there's 5 valence electrons. So overall, I should have an electron count of 10. That's my goal. I wrote my skeletal structure here because I know carbon is the least electronegative, and hydrogen can't be my central atom. So I'd have to go with carbon here. In terms then of my skeletal structure, I just took away 4. So that means I have 6 more electrons that need to go here somewhere. And remember, the rules say I have to fill out the outer ones first. Well, hydrogen's good, so that means I'm going to give nitrogen those 6 electrons. But let's look at my central atom. Does the central atom carbon have a full octet? It does not. It needs to get a full octet. It's not going to get anything from hydrogen because hydrogen's already good to go. But it could share that with nitrogen. So if it does that, I would get HC double bond N. But that's still not good because carbon still doesn't have a full octet. So I need to do one more. Nitrogen's going to still share, and carbon's going to be a little greedy and try to take that electron pair. So they're going to share that, and that's going to give me HC triple bond N with my 1 lone pair. So that's why we see this one right here in terms of forming multiple bonds, okay? Guys, on this one, these are some practice problems in terms of drawing Lewis structures. You should also complete these. I will check them tomorrow at the beginning of class. So right now, you have 2 slides that you need to have done for me at the beginning of class. This one, and then you also need to have the one with that last dipole moment question, okay? So writing Lewis structures, we also want to assign formal charges. By assigning a formal charge, we are trying to determine the stability of a Lewis structure. It is super imperative that every time you draw a Lewis structure, you do the formal charge. Your AP chemistry curriculum says they will not ask you a single question, like a question alone, find the formal charge of this Lewis structure, or the atom, maybe carbon, in this Lewis structure. They're not going to ask you that. Instead, they may ask you to draw the Lewis structure that is the most stable. And the only way that you can figure it out is if you find or assign a formal charge to each element. When we do formal charges, we want to count the electrons in lone pairs and half the electrons that it shares with other atoms, like when it's in a bond. And then we're subtracting that from the number of valence electrons. So if we're looking at carbon dioxide here, so carbon, it has 4 valence electrons, so I wrote the 4 there, and it's 1, 2, 3, 4 directly around it because it says half the electrons it shares with other atoms. So 4 minus 4 gives me 0. If I do the same thing for oxygen, it has 1, 2, 3, 4, 5, 6 electrons around it, so that also gives me a formal charge of 0. We would prefer all of them to have formal charges then of 0. That would be like the best stable Lewis structure. And so I know over here that that Lewis structure isn't correct because I have oxygen here being a -1, but oxygen on this side being a +1. So I know that that's not a correct Lewis structure. So the best Lewis structure is the one that has the one with the fewest charges. So we would love it if they would all have a formal charge of 0, but they don't always all have all 0 formal charges. Instead, we want one that has the fewest formal charges. And we also want to make sure if there are formal charges that are present, the negative charge should be on the most electronegative atom. So if we look at this, for example, I have nitrogen and carbon and oxygen all bonded. So in this case, nitrogen is given an overall -2 charge, carbon is 0, oxygen a +1. oxygen in this whole entire compound should be the most electronegative. So the fact that it has a positive 1 charge should have a negative charge, if anything. So this would be a really, really, really bad Lewis structure. If we go over here to this one, nitrogen would have the -1, carbon was given a 0 formal charge, oxygen has a 0 formal charge. In this case, nitrogen is not more electronegative than oxygen, so this also does not place the negative charge on the most electronegative element. But if I go over here to this one, nitrogen, 0 formal charge, carbon, 0 formal charge, oxygen, a -1 formal charge. That is the most electronegative element. That is the one that should, if any of them, would have a negative formal charge. So this structure would be the correct one. We can do this one together in class tomorrow. So right now I need you to remind me, slide 25, slide 33, this question here. So slide 25, slide 33. Someone keep track of that for me. So this is the Lewis structure that we would draw for ozone, which is O3. And we're getting into something that's called resonance. Well, my double bond, doesn't matter where the double bond goes. It could go over here, but could I also draw a Lewis structure where the single bond was here and the double bond was over here? You absolutely could. It's crazy not to. So this is what we draw for our Lewis structure, but it's not what we observe ozone to actually act like. Instead, the oxygen bonds end up kind of being the same length. So the length between these two and the length between these two are the same. But they technically shouldn't be, because this one is a double bond and this one is a single bond, and double and single bonds can have different bond lengths here. So I observe, though, actually in nature, ozone, they have the same bond length between those oxygens. So why is that? It's because of something called resonance. So one Lewis structure may not be able to accurately depict a molecule like ozone. Instead, I could have the double bond placement here or the double bond placement here. So what we find in real life, in actuality, is that ozone, here's my double bond on this side, it could have another resonance structure with a double bond on this side, so there's kind of like mirror images of one another. So if I'm thinking about those resonance structures, it's actually kind of like a synthesis of these two. So it's really like I'm taking both of them and thinking about like the average of these two, which is why then I get the distance between those two O bonds to be the same. Because in this resonance structure, I'm really taking both of these two things into account, kind of meshing them together, which is what we see here. So they kind of tried to give you like a color example of what ozone actually looks like. So just as we think of like green is made from blue and yellow, I can think of these two resonance structures coming together to form kind of like an average of just those two. I'm kind of adding those two together to get my ozone molecule of what we actually observe. And we're going to start here, guys, tomorrow in class, because I think that this video is probably long enough, yeah. So we'll start here tomorrow in class 38. So you have to remind me, slide 25 and slide 33. We have to do those tomorrow. Okay, have a wonderful night. Bye.